Zero. Hi, everybody. Welcome back to the Astro Imaging channel on this Sunday night, the first full night of NFL action. We have something else for you today.
It's not working.
For those of you who may have been watching.
Stop, Alex, please. It's not working.
Okay. Eric, it's not working from what you can see.
The video's not coming through.
No, it's black screen.
But the audio's coming through. That's weird. Tim, do you want me to
It's on now. I got it.
Okay.
Hi, everybody. We're back. Hi, everybody. Welcome back to the Astro Imaging channel. It's the first Sunday of NFL football. The National Football League is back. So you may be distracted, but this is more important. This is your Sunday night Astro Imaging Club meeting, the Astro Imaging channel. And we're so glad to have you back. We've got some things happening for you, and I do need to tell you about those things. And so I'm going to present my screen and click over to the Astro Imaging channel. And, oh, I'm not there yet. I want to go over here. We've got two projects going for you. Nebulae, the beauty of dust. And you click on TAC shots up here to get into that. And then Eric Coles has his M33 processing data out there. So if you go to TAC Workshop, you get into that. You can go get all of this data, and we really want you to go do that. Go get the data. It's good, clean data, like all of Eric's data, and it's so much fun to process clean data. So you link to the data files here, download them, and then when you're finished, click here to submit the file, and we're putting the show together sometime. You got till October 17th, so it's a little more than a month to do that, and then we'll have a show sometime in November or something like that to show everything that's gone on. And we also have, if you go over to the tech shots, you can submit your images of nebulae, and same kind of thing, and we'll make a movie out of it. Arno's going to be hard at work at that. So we hope you enjoy that. And I also like to go during this portion of the show, just real briefly go through the calendar a little bit, get you excited about some of the upcoming shows. And tonight, Glenn's going to tell us about imaging through the light dome, which will be pretty cool. And then Queeve, the Lazy Geek, is going to be here next week. He's put out a lot of really good videos, and a lot of people really like them. Queeve, are you still here with us tonight? Can you?
I am here.
What are you going to talk about next week?
So next week, we're going to talk about imaging in difficult conditions, which does include something similar to Glenn, imaging through a light dome, but some other stuff, other tips and tricks, and probably a lazier way to go through things, since I do like to be lazy. But yeah, I'll make sure that we don't cover too much of the same ground.
Yeah, just what I need, more help being lazy. And then I go back to sharing again. And one of the things I should tell you is that just by a quirk of the way things are, Linda is coming in on October 3rd, and she's going to be quantifying the effect of dark skies, which is somewhat related to what Glenn is talking about this week and Queeve's talking about next week. And then when I was visiting my cousin back last summer, I found Gian Lorenzo Ferretti. He was in an article in the Chicago Sun-Times, and he's talking about imaging from the city. So he'll be here November 7th. So we've got 4 topics talking about it. And when we were talking in the warm-up before the show, we said, wow, that's a lot, huh? And as Glenn pointed out, yeah, that's because we all need to know about this kind of stuff. But we've also got one of the people that keeps PhD running coming in next week. Peggy Walker will be here, not next week, on October 10th. Peggy Walker will be telling us about tactile astronomy resources for the blind and disabled, and how to use our images to help people that may be a little bit handicapped to enjoy the night sky. But you can see that while we're good until November something, actually I think we're good until December, we start having problems after that. Okay, we don't have any more dates after that. So you need to hit the presenters, the contact link here, and tell us that you'd like to do a show for us. and tell us what you'd like to do it about. And we'll talk to you a little bit about it, and maybe we'll put you on the show and you can share your knowledge. Remember, you're an astroimager. That means you're pretty smart. And you can do things that the average guy can't do, the average girl can't do. Because you're smart and you know how to handle technology and stuff like that. You are capable of putting on a show. If you've done something in astroimaging that you'd like to tell other people about, or you see people, struggling on something, you need to pitch in on the Astroimaging channel and do your thing. Okay. So contact us and get into it. Now, I asked Glenn to be here because I know Glenn puts out really good images. I see him on occasion, and I'm going to ask Glenn to go ahead and take over while the rest of you guys all go out there on the Astroimaging channel on YouTube and ask your questions of Glenn as we go along. Glenn, you ready?
I am ready.
Okay, take over.
All right. Okay. You seeing my screen?
I'm seeing it. It's not presenting yet. Here we go. Play or whatever you do.
Yep. There you got
And
that.
now it looks like you're presenting.
Okay. Well, thank you very, very much for letting me be here. I've been watching the Astroimaging channel for years, and I've learned so much from it, and it's an honor to finally be presenting on it. My name is Glenn Diekmann, and I'm going to be telling you about imaging through the light dome, or doing astrophotography from a light polluted place or a light polluted sky. Here's the outline. I'll start by giving a little bit of information about myself and the location where I do most of my imaging from. I'll tell you about the problem of light pollution, where it is, why it is, and then I'll get into the heart of the talk, which is the strategies to mitigate the effects of light pollution. Things that I've discovered or learned along the way to make it just a little bit easier. I will be presenting examples from my own work along the way, and then at the end we'll wrap things up and hopefully tie it together. Feel free to stop me at any point when there are questions, okay? And we'll also have time for questions at the end. All right. So a little bit about me. My background is in medicine. I'm not an engineer or a physicist, and I mention that only to say that I didn't intend this talk to be a super technical one. I tried to make it accessible and practical. So that's been my approach. I live in the Los Angeles area, and Los Angeles is a pretty big city with a lot of light pollution. I have always been enjoying the night sky, always looking up and wondering what was out there. And then finally, when I was in 2015, I guess about 6 years ago, I found a guy who was selling a Celestron 8 SE in my neighborhood, and I bought that thing and I set it up on my lawn. And it's a go-to mount, and it has an alignment routine that asks you to point the scope at 3 bright objects. Many of you are probably familiar with this. So it didn't ask for stars, or I didn't even have to know what the objects were, just 3 bright objects. And lo and behold, that's what I saw in my eyepiece. And my mind was completely blown. I was, I guess, expecting to see a star. I wasn't expecting to see a planet, let alone a planet with rings. And it was just the most amazing thing I'd ever seen. And in my mind, this is how it looked, and it left a lasting impression on me. I've been into astronomy ever since, and I love visual, I love imaging, but because of light pollution in my area, I tend to do a lot more. I tend to do a lot more of the imaging. So I belong to the same astronomy club that Alex McConaughey belongs to, and it's called the Riverside Astronomical Society, and it's a great club, and they have a wonderful dark site called GMARS, and it's wonderful, and I enjoy myself every single time that I go there. Unfortunately, because of work and family commitments, I just never seem to be able to get out there more than a couple times a year or so right now. So as a result, I do most of my imaging from my home, from my backyard. So I think it's important to show you where I image from so that you can understand the context of my experience and the things that I'm telling you. All right. So this is the side of my backyard looking to the north, and my roof line is over here on the left. My neighbor's roof is on the right, and there's a great big hedge on the north end of it. And that gives me this sort of strip of the sky looking northward. And looking southward, it's kind of the same thing. I've got, it's reversed here, but you know, roof line, and, you know, and that's it. So I call this my alleyway view of the sky, or my bowling alley view of the sky. It's a narrow strip, but, you know, it could be worse. I can see things pretty far to the north. I can see objects pretty far to the south, and I have a pretty good view through the meridian, which is what you know, matters for imaging anyway. So I'm not complaining. However, when I look to the south, I really have problems with light pollution, and the reason for that is I live in a sprawling metropolis. That's what Los Angeles is. And I've circled the city there, and that's me, the blue dot, about 30 miles away or so. But everything around it is just densely packed, a high density population. And what I'm showing you here probably represents 10 or 12 million people. So it's congested, and it is bright. The night sky is very bright. And what I'll draw your attention to here is I'm on the edge of a mountain range, and that does give me some reprieve from the light pollution. I have a somewhat darker sky looking northward, but anything to the, you know, to the west and to the east and the south, I'm dealing with all of this, and I suspect that many of you are in a similar situation. Here's the street I live on, and the first thing you notice is the bright street lights, bright unshielded street lights shining, you know, not just the ground, onto the ground, but into the sky laterally. There's a lot of landscape lighting. And the sky is just a pale, featureless thing with, you know, some stars you can probably make out, but not a whole lot. And it's pretty bright near the horizon there. And this would be looking kind of west by southwest. And that's Los Angeles, sort of in that direction. So, and here is, so this is the same, this is, I showed you where my scope was on the side yard. And this is actually during an imaging session. This is about midnight. And what you notice here, it's a little bit underexposed, but what you notice here is just how gray and bright the sky is. And in case you can't see my telescope, there it is. And you can probably make out the bright LED of my mini PC sitting on top of the scope. But that's a really bright, gray, featureless sky. And just for reference, here's Jupiter. Jupiter is one of the brightest objects in the night sky, and it shows up as this faint little dot, you know, in from my backyard. So, as I said, that's what I'm dealing with. I suspect that many of you are dealing with the same sort of thing. So, what's the problem? Light pollution is the problem, and it is caused by too much outdoor lighting and the wrong kind of outdoor lighting. What do I mean by the wrong kind? Well, I just showed you the wrong kind. The lights that are not shielded, they don't just illuminate the thing they're supposed to illuminate, but rather they send a lot of light in directions that that don't help lighting the intended source. So straight into the sky, to the side where it contributes to glare, that sort of thing. And when you take a lot of people and you put them in an urban setting and everyone has outdoor lighting, this is what you get. And the picture to the right shows kind of the worst case scenario of that. Well, I would say 80% plus of the world's population lives in urban areas or suburban areas. And as a result, about 80% of the population cannot see the Milky Way at night. And I couldn't either. I mean, I still can't, but I didn't see the Milky Way until my wife and I went to Hawaii 12 years ago or so. That was my first time seeing it. And that's a shame, as it's breathtaking. But the sad reality is that most people can't. Here's an interesting picture that I found on the International Dark Sky Association website. And apparently there was a huge power outage in 2003 that affected 50 million people. And the lights across multiple states just went out. And this picture on the left was taken before the power outage, and the one on the right is after. And I don't know about you, but I would never have guessed that on the picture on the left that the Milky Way was stretching just above that house. So this, to me, really drives home how much the light pollution is depriving us of our view of the night sky. This just shows, urban centers are bright. There's in every major country, they've got big cities, and big cities have lots of lights. And so this is kind of a nighttime satellite view demonstrating that. This is my neck of the woods again. This is essentially the same map that I showed you earlier of where I live, and I'm behind the target here. And it's bright. There's lights in every direction, except, as I said, to the north, I get a little bit of a reprieve because of the mountain range that's behind me. Alex McConaughey is out here somewhere, so he's got it pretty bright as well. All right. John Bortle is an astronomer and an astronomy journalist who proposed a scale for rating the darkness of a sky. And it goes from 1 for an excellent, pristine dark side all the way to 9, which is basically your inner city sky that's almost white and completely featureless. And then there's, variation in between. My sky is about a 7. So take that. Everything that I'm telling you is, from the perspective of someone who's in a sort of a Bortle 7 sky. All right. Now, I want to be very clear that there is no substitute for a dark sky. The pictures that I get at GMARS or other dark places they just always seem to be a little bit better than what I can achieve from my backyard. Say, for example, you take a 1 hour exposure at a nice dark place with sky brightness of say 21.8 magnitudes per arc second. That's a pretty dark sky. If you go to a place that's only 1 magnitude brighter, you would need 2.5 times the exposure to get the equivalent image or the equivalent image quality. If you go someplace 2 magnitudes brighter, you would need 6.3 times. And I'm right in here at the 18.8 to 19 range, so I'm somewhere in between. 15, almost 16 times brighter, and all the way to 40 times brighter for a 4 magnitude difference. And, even when I say equivalent image quality, I mean, it's never going to be quite the same. But this just drives home what a big difference having a dark sky can make. So those of you who have a dark sky, I hope you appreciate it. All right. So that brings us to the strategies. How do we deal with this problem? First, I'm going to tell you about signal to noise ratio, because everything sort of boils down to optimizing your signal to noise ratio. So SNR and signal to noise ratio, I'll be using those interchangeably. For the purpose of this talk, signal is simply useful information. And specifically, it is the light that is coming from your target, whatever you're taking a picture of. That's what you want to put on your camera sensor. That's the signal. Unfortunately, that always comes with noise, and noise is uncertainty in that signal, and it manifests as a graininess in the pictures that we take. So signal and noise are inextricably linked. And when you add signal, you will always add noise. However, there is an important relationship to understand between the two that we can exploit for the purpose of astrophotography. The signal adds in a linear fashion, but the noise adds with the square root of the signal. And what that means is, as you collect data and you you add to your data, your signal is going to build and build and build in a more or less linear fashion, but your noise, although it will add at a slower rate. And therefore, the difference between the signal and the noise will increase, and you'll get an increased signal to noise ratio. It's a pretty deep topic, I discovered in researching for this talk. And there are, it's pretty math heavy, theory heavy. And I don't intend to get into that, but I refer you to the excellent talks by Doctors Craig Stark, Robin Glover, and others if you're interested. This diagram just depicts what I was trying to explain in the previous slide. The signal will build linearly, but the noise, although it builds more slowly, so you get an increase in the ratio between the two. All right. So the goal of dealing with light pollution, in fact, it's true for all of astrophotography, is you want to optimize your signal to noise ratio. And I like to distill things down to their essence whenever I can, because it helps me understand them better. So the way I think about optimizing signal to noise ratio when I take pictures is I want to, number one, collect my photons efficiently. I want to collect lots of photons. And then I want to collect photons that I'm interested in. So by that, I mean the photons coming from the target and not necessarily the photons coming from the sky. Okay, so I'm going to tell you about collecting photons efficiently first. All right. So there's two ways to do this. There's probably others, but these are the two that I've identified. You can do it better with a fast telescope and with a sensitive camera. Okay, so I'll start with a fast telescope. What do I mean by that? Well, to understand, you need to first understand what, excuse me. You need to understand focal ratio. And focal ratio is the relationship between focal length and aperture of the telescope. And it's expressed as a number, an F number, like f2.8, f6. You've probably seen such numbers if you're doing terrestrial photographies. It's the same thing. And the importance of it is it determines how much light from the telescope falls on each pixel of your sensor. Okay. And for the purpose of the talk, I'm going to be calling things less than telescopes with an F ratio less than F5 to be relatively fast, and those greater than F5 to be relatively slow. And in deep sky imaging, we tend to use at most a ratio of F10, F11 maybe, and it's usually a lot closer to F5 and lower. All right. This diagram, I think, really clarifies the idea. So on the left, we have an F10 optic, and that's, a relationship. So the focal length divided by the aperture in this case is 10. And what you can see, and there's the sensor at the bottom, and what you can see is that the light entering the funnel, if you think of it as a funnel shape, the light entering it doesn't really collect much of the light because the funnel is quite narrow. Now, by doubling the aperture, we produce an F5 optic, and that really broadens the opening of the funnel, and it's able to collect a lot more light and focus that light on the sensor. In astrophotography, we don't do that so much. We don't routinely increase the aperture of our telescope. That would mean basically changing telescopes. But what we do commonly do is we change the focal length of our telescopes with focal reducers. And that ends up doing the same thing. You can take an F10 and turn it into an F6.3 or something like that by shortening the focal length. But it wasn't as intuitive in the diagram, so I went with this one. But astrophotographers tend to do it the other way. All right, so a lower focal ratio is good. It's a good thing. And as I said, it concentrates more light onto each one of your pixels, and it results in shorter exposure times. And it will produce a wider field of view and a decreased object size on your sensor. And that may or may not be a good thing, depending on what you're trying to achieve. And it will give you a better signal to noise ratio. Okay, so that was how to collect photons with a faster telescope. Now let's talk about a sensitive camera. First, we need to understand quantum efficiency. All right. So the light enters your telescope and it goes through the optics and then it hits the sensor. Some percentage of those photons will be converted to electrons, which becomes signal that the camera can use to produce an image. And quantum efficiency can be thought of simply as electrical sensitivity to light. And it's expressed as a percentage of photons converted to electrons, okay, on that sensor. This is a quantum efficiency curve for a variety of sensors. And what you see here along the bottom x-axis is the wavelength of light, and then the quantum efficiency 0 to 100 on the y-axis. And every one of these sensors has, I want you to notice, a peak quantum efficiency. Okay, this is hovering right around 78%, 80%. For the one in green, that's the Sony 674 CCD. And then there are other ones that are much lower, right? So a peak efficiency of 40, 45%. So, and it also falls off in the very short wavelengths and in the very long wavelengths. Okay, here's another view, and this is a mixture of Kodak or onsemi sensors, as well as some Sony sensors. And again, you see the variation with the peak. But there's also these lines, and I want you to pay attention to these for a moment. So this is O3, that's HA, and this is S2, and those are specific wavelengths that are very important to astrophotographers and to astronomers in general. All right, and a given sensor might be very sensitive in one, but less sensitive in the other. And if we compare a couple of them, like this is the 8300, that's it's ubiquitous. It's been out for years, and I have one of these as well. But its quantum efficiency in the S2 wavelength is only 40%, and then 44% for HA. O3 is only 48. Compare that to the Sony sensor, and you got 61, 65, 76. So judging based on that alone, it's a much more efficient sensor. Now, sensor efficiency is very, very important, and I've found that it helps me to collect photons more efficiently, for sure. But it is far from the only consideration. When choosing a camera, you have to look at image scale and sensor size, pixel size, full well depth, and read noise dynamic range, and other things. So obviously there's a lot more to it than that. You don't just want to pick the most sensitive camera, but it's just one thing that you can look at if you're trying to be more efficient with your photon collection. All right. Now let's talk about collecting lots of photons. So astrophotographers don't just take a single picture of an object when it's up in the sky. They take many, many pictures, sometimes over multiple nights, until they have hours and hours worth of pictures. And then through a process called stacking, they integrate these pictures into one master image. And stacking takes this information from the individual images and makes a new image with a much higher, in some cases, signal to noise ratio. Okay, so stacking will give you a higher signal to noise ratio. And along with that, you get noise reduction. Okay, that goes hand in hand with that. And the relationship, again, like I showed you earlier, it's the square root of the number of frames stacked. So sound familiar? And this is how it looks. Let's say you have 2 frames instead of 1. You're going to reduce your noise by 1.4x. 4 frames gives you 2x reduction, basically cutting your noise in half. And so forth. 25 frames gives you a 5-fold reduction in the noise, and then finally 400 frames giving you a 20-fold reduction in the amount of noise. And it's a very powerful effect. So I'll show that to you now. Here's an example. This was, this is again, taken from my backyard. This is Andromeda, the Andromeda galaxy. And this is a single frame with my 8300 sensor, 60 seconds. And this is the kind of thing that doesn't come through very well on YouTube. So I apologize in advance. But what I'm seeing here is that the background has a lot of graininess to it. And, you know, you can tell it's a galaxy and all that, but it's, you know, not very bright. The details are faint. Okay. Bringing it to 4 frames, and what you see is the background really becomes smoother and the object itself becomes much brighter. So there's 1 frame, 4 frames, 1 frame, 4 frames. Going to 16 frames halves the noise again. So 4 frames, 16 frames. I mean, that's a pretty big jump, I think. And now we're starting to see nebulosity all the way out to the edge of the galaxy. And the background is looking much, much smoother. All right, and here's 200 frames. That's about a 14-fold decrease in the noise. Okay, and I know that's hard for you to see. So maybe you can see it a little bit better if I show it to you this way. So up here, it's grainy, and you can see this is sort of the upper left edge of the galaxy that I'm showing you. So this is, you know, pretty dark, kind of grainy, a little bit brighter down here. Going to 4 frames, it's a little smoother, you know, and getting a little bit brighter here. But by 16 frames, I'm starting to see things up here that I did not see over here. And that's what I meant when I said earlier that that noise is uncertainty in the signal, because you can't tell if you're looking at what these grains represent. Is there something really behind there, or is it just bad information or noise? By the time you get to here, you can see that, yes, in fact, there is nebulosity right here. I would never have guessed that from this first one. And then finally, by the time you get to 200 frames, what I'm looking at here essentially shows no noise anymore. And not only can I see the nebulosity, but I can start to see some nice, dusty details in there as well. So, you know, stacking gives you this amazing improvement in signal to noise ratio. Your noise goes down. It's, in my opinion, it's the best form of noise reduction. All right. Now let's talk about collecting only the photons that you are interested in. And by that, I mean, wouldn't it be nice if you could collect only, you know, put on your sensor only the light leaving your target and none of the light that's coming at you from the sky glow, in other words. So that's what we're going to talk about next. Okay. First, we need to talk about just real quickly about how this works for certain objects. And I want to be clear, this works for certain objects and not for other objects. All right. But imagine that you have a bright star that's in a cloud of gas or next to a cloud of gas. And the bright star really has a lot of stellar wind and radiation coming out of it. And some of that radiation hits the gas cloud, and it hits the atoms or the molecules of the gas cloud, and it will excite some of the electrons in that gas cloud. And those electrons will go up to a higher energy state. All right. And then they will relatively quickly drop back down again. And when they do that, they produce or they emit a photon. And the reason that's important is when you drop from one energy level to another energy level, it's always the same energy value, and the wavelength of light that's emitted is always the same. And that's called emitting a photon, and that's why we call these types of nebulas emission nebulas, right? Now, looking at the spectrum of hydrogen, so you've got your full spectrum of light up top, but I want you to focus down here. There's only 4 lines. And these are the very, very tight specific wavelengths that hydrogen will emit photons at. So imagine if you had a filter that could let just this through and block everything else. That would seem like magic. And in some cases, it works almost like that. All right. Now I need to tell you about broadband versus narrowband images. So the trick that I just showed you, or the concept that I just showed you, applies only to certain types of objects, and specifically those emission type objects. Okay, broadband objects emit the full spectrum of light, and narrowband objects only emit light mainly in those specific emission lines that we talked about. Broadband objects include stars, galaxies, reflection nebulae, dark nebulae. And then on the narrowband side, I already told you about emission nebulae, but there's also planetary nebulae. And it sort of the same principles apply. Okay. These are the narrowband filters that most people use. There's one for oxygen, one for sulfur, and one for hydrogen alpha. And there are other specialty ones, but these are the ones that most people doing narrowband imaging are using. And you can see off on the right column, the wavelength is very specific, 500.1, 656.3. So they block all other light except a narrow band pass just around those frequencies. Okay, so what does that mean? Now I think an example or two is in order. What I'm going to show you is some of the images I've taken, or at least some of the data that I've collected from my backyard. And I'm going to show you first some RGB data, okay? And here's the first one. I'm going to show you RGB data, and then I'm going to show you kind of an equivalent set of narrowband data for the same target, same framing, everything. All right. This is RGB 45 minutes per filter. And this represents a simple histogram stretch in PixInsight. I didn't do anything to it. I didn't reduce gradient, nothing else. All right. Okay. So here's RGB, and there's narrowband. 45 minutes per H, S, and O. Okay. I chose a palette that looks a little bit more natural just to make it more directly comparable to the RGB, but I think the point is made. So what I'm seeing here is just a lot more definition, sharper edges, a lot more dusty detail, and even the ugly gradient over here goes away to a large degree. You don't see it over here because it's being filtered out. So your narrowband filters are getting you a lot of mileage. Here's another example. This is Fleming's triangle or Pickering's triangle in Cygnus, in the Cygnus loop, and it's part of a supernova remnant. The RGB version is pretty good, you know, for only 45 minutes. I mean, I can see all the nice red hydrogen. I can see the teal blue oxygen signal. So, I mean, it's not bad, but I mean, it's just no comparison to what you get from narrowband. So, you know, RGB to narrowband. And to me, this is, I mean, it is almost, you know, magical. And to do this from a light polluted place is just incredible. So, so that's narrowband filters. Okay. All right. So other tips, maximize the amount of time that you spent on target. I already told you that as you collect more and more data, you get an improved signal to noise ratio. But what if you're setting up every night? If you set your gear up every night and you have to polar align and you have to, you know, troubleshoot and all that, you're probably not going to get all that much data. So my first recommendation or suggestion for you, if you can do it, is find some way to have a permanent or a semi-permanent setup. Now, I don't have a permanent setup. I do something a little different that I'll mention in a moment. But if you have an observatory, or if you can make yourself an observatory, that's amazing. You should do that. A pier would help tremendously. Or do as I do and just kind of leave your setup out for multiple days at a time. And I leave the one, you know, this setup, I leave it out for 2-3 weeks at a time sometimes. And I just use good scope covers, just a Telegizmos scope cover. And I have one for the, you know, for the OTA as well. And my stuff does great outside. So that lets me image night after night after night on a target and get enough good data that I have something to, to work with and really turn into a nice picture. What goes hand in hand with that is automation. And I think that everyone who's interested in doing this kind of thing needs to automate. We're very, very fortunate to have so many excellent programs these days. There's Voyager and Nina, Sequence Generator Pro, and Maxim DL. I mean, there's really an amazing selection of session management software out there. And I have set mine up. I use Voyager. I've set mine up to be basically one click before sunset, and my scope wakes up at the right time. It does its autofocus routine, and it aligns to the target with pixel accuracy. And I wake up in the morning and there's data on my hard drive. That to me is amazing. Furthermore, it lets me make a choice what I want to do with my time. Sometimes I'll sit out there with binoculars and I'll just look at stuff, and I love doing that. Other times I'll go on date night with my wife, or I'll watch a movie with my kids. So it's nice to have that automation capability. Another tip is image around a new moon. The moon is the biggest natural light polluter that's up in the sky. It reflects 12% of the sun's light. And if you're struggling with light pollution to begin with, don't add to it by shooting around a full moon. Wait for the new moon, or at least on either side of the new moon. I'll usually start imaging around the last quarter, and I'll go all the way through the first quarter. And if I have narrowband imaging to do, I'll do it when the moon's a little bit brighter, and I'll save my RGB imaging for when it's a new moon and there's no moon out at night. All right, choose targets that make sense for your sky. I see so many wonderful pictures, people with scopes in Chile and other dark places, and they're just amazingly deep, and they have so much fantastic dust and details that I would love to bring out in my own pictures. And then I go and I try them, and I just can't do it, or at least not to the degree that they're doing it. And the simple truth is certain targets really can't be done from a light polluted place as well as they could be done from a darker place. So objects that make sense from a dark sky include globular clusters, open clusters, bright emission nebulae. Those are all good choices. Dark nebulae, the faint stuff, probably not. And there's even a limit, I think, to what you can do with narrowband filters in light pollution too. All right. And my last tip is to upgrade yourself. And what do I mean by that? This is a challenging hobby, and it requires a lot of effort and a lot of learning and a lot of practice to do right. And I see from time to time on Astrobin or elsewhere images that are taken by people who have some really fancy equipment, very expensive equipment, but the images themselves are a little bit lackluster. And that's fine. I'm not saying that everyone should have images that are a certain standard. And if the person's happy with the quality of image, that is absolutely all that matters. But my point is, you don't necessarily need the fancy equipment to get the nice image. And I think of it as learning how to play a musical instrument. For example, this guitar. If you hand a mediocre guitar to someone who really plays well, they're going to make it sound amazing. And conversely, if you take a premium guitar and you hand it to someone who doesn't really know how to play, it's just not going to be a good result. And I think it's the same thing with astroimaging and many other things, frankly. So practice. Learn PixInsight, learn Photoshop. I was intimidated by PixInsight, and I put it off for a long time, for several years. And then finally I jumped in, and you know what? It was something that wasn't all that hard to learn. There are some amazing tutorials out there, and it's made a huge difference in my processing. I mentioned some of these things. There are some excellent books. There's free online tutorials. Light Vortex Astronomy, I think, is one that I used early on. And then there's some subscription video libraries. I use Adam Block's all the time. I've also used Warren Keller's. And when you consider how much we spend on this hobby, I mean, thousands or tens of thousands or more than that, the cost of a subscription is really pretty trivial. And I have learned, so much from, from some of these videos. And I just consider it to be one of the best investments you can make in your astrophotography. All right. Hey, do we have any questions at this point? Am I doing okay?
Yeah, no questions yet.
Wow. Everything's that clear, huh?
Yeah,
Okay.
no, we've had about 80 plus people watching, which is a pretty good night for us.
Okay,
And
good.
there was a few comments about the light pollution where we live and stuff like that, and a few other stories. But everybody's just been fascinated with listening to you give your advice there. Hey,
Okay.
I got a question. I got a little question for you.
Yes, sir.
You were going through your list of ideal targets immediately after you did narrowband. Can you tell us about what the effect of narrowband is on some of those targets? For instance, globular clusters and narrowbands, I've just never put them in the same bag. So maybe you should explain a little bit about that.
Well, I think what I meant to say was certain targets are not suitable for narrowband. And I wouldn't, for example, try to shoot a globular cluster or a galaxy through a narrowband filter, because it's just, those are broadband objects. They're producing light across the whole spectrum. And it's just not going to look right if you try to image it through a narrowband filter. So yeah, sorry if I didn't make that clear.
And the other thing is that you are using monochrome with various filters. You're not using one-shot color with one of those tripads.
I totally forgot to mention that. Yes, this is this is mono camera and filters.
Okay.
Yes.
Glenn, I think there's probably one more thing to mention. I had to switch mics. I hope you can hear me. But
yes, I can hear you.
It's a fairly easy calculation. If you look at, say, a red filter, which will capture all the light from an emission nebula, it's about, let's say, 125 nanometers wide. If you have a 3 nanometer filter that just gets all the emission, you're only getting 1/4 of the light pollution, but you're getting all of the red. And that's kind of how that works. It's not just that it's narrow, but it's eliminating everything else.
Everything else.
So you don't get more red signal. You just get, 1/40th of the light pollution that you would normally get even with a red filter.
Yes. No, that is an excellent way of saying that too. But yes, that's absolutely the case. Well said. All right. Shall I carry on?
Yeah, please go
Okay.
ahead.
All right. So
Wait, Glenn. I'm
yes,
sorry,
sir.
Glenn. We forgot to tell you in the warm-up that we turn our microphones off when we're not talking. And so if you say any other questions, and like I was fumbling for my mic button.
No, I knew that.
Anyway, there was a question.
It was just eerily quiet. That's all.
Yeah. There was a question from, who was it? Renan van der Wingard. How about taking hydrogen alpha with the full moon or at a target that's 45 degrees or more away from the moon? Have you had any success with that?
Yeah, I've done it. And I showed you my view to the south. I mean, it's, I've got terrible light pollution out that way. And I've taken some low objects. I mean, with a declination of, what would it be? I mean, something that's only like 26 degrees over the horizon, for example. So low. I mean, more than like a two air mass kind of a situation. And I use narrowband. I mean, that's the only way I can shoot to the south and get a decent image. I really can't do RGB when I'm pointing really low in the south. It's just the light pollution is overwhelming.
Okay. And you're lucky you've got a national forest to the north, I pointed out earlier.
That is fortunate. Yes.
Yeah. But is it Jeff wants to know? No, Jeff commented that he wished that we didn't have broadband LED lighting, but rather had selective parts of the spectrum. But John at Astra wants to know, what's your exposure length? How do you optimize exposure length?
That is a very good question. And there's a lot of discussion about that on the forums. I will expose to get my background over the read noise, and I do a simple calculation for my camera to kind of figure out what the read noise is and how much over the bias signal. In other words, the 0-second exposure signal for my camera would have to be in order to kind of drown out that noise a little bit. And then I consider my target. If I'm shooting a target that has relatively few stars, I'm inclined, or at least not very bright stars, I'm inclined to let the exposure maybe go a little bit longer, as long as I'm not blowing out stars. Once you start blowing out stars, you start to, you start to clip them, and that hurts your star color. So for me, it's a little bit of a, maybe do some calculations or just know your equipment to know where to start your exposure. And then I just adjust. I do a few, when I'm starting on a target, I'll do a couple of trial exposures just to see, how they look. And I've even found that during an imaging run, let's say I'm collecting O3 on something, and I've got a 3-minute exposure set up, and it looks like it's kind of borderline, maybe a little bit underexposed. I'll go to a 4-minute exposure next. And so there's always a little bit of trial and error for me, but I want to make sure the background is bright enough, the sky, that I'm drowning out my read noise, and I want to make sure that I'm not clipping too many stars. And beyond that, I don't get too fussy about it.
The Astronomical League has a program called the Urban Observer, and it suggests that it has targets that you can see from the city. And they also have a list of suggestions there as to that you observe after midnight, because the stores close down and the traffic's less and there's less light pollution, so you've got a better chance of seeing things. I don't buy it. Have you ever noticed whether there's a change in exposure values caused by the cycle of life taming down and people turning off lights?
There is a little bit in my area anyway. I do have a sky quality meter, and sometimes I'll just check it at the beginning of an imaging session, then a little bit later in the night if I happen to be walking out to check on my rig. And not always, but sometimes it's like 1/10 of a point lower. I mean, who knows if it makes a difference in the final image, but I'm more concerned about total imaging time. So I start generally at astronomical night, and when my target clears my neighbor's roof, and that's when my imaging session starts, because I don't have a huge view of the sky. I've just got that little narrow alleyway, like I said. So I'm more concerned about just getting on target as early as I can, imaging night after night, and then I will weed through my subframes in PixInsight later to pick the quality ones.
Okay. Eric, do you want to take the questions that have come in while we've been talking? Lanceman and Martin have a couple of questions.
I have to click my microphone button as well. Narrowband filters, how narrow as it relates to the difference in Bortle scale? Not sure what that question is, but that's how it reads.
Well, I think they're asking, how narrowband filters are sold as 12, 12, 7, or 3s. Which one is better, and how does it relate to your light pollution situation?
Well, that the narrower the band, the more expensive the filter by a significant amount. But
Right.
The narrower the band, the higher the ratio of emissions that you see versus the background and the stars. So I think they've kind of priced it. They know a narrower band filter is going to cost more because it gives you a better result. So I think my recommendation always is get the narrowest band filter you can afford.
Glenn, have you what are your what's the bandwidth of your filters?
I use 5 nanometer, and I had 3 nanometer, but then I switched to faster telescopes with f ratios less than 4 in some cases. And what I found was I was actually clipping part of that bandwidth, and I was getting less signal with my faster scope than I had with the slower scope. So the band pass that each filter gives you, it shifts a little bit depending on the focal ratio of your scope. So if you have a longer focal ratio or a higher focal ratio scope, you can use any band pass filter that you want. I mean, you can use 3s, no problem. But as you get down close, below 4 and close to 2 or whatever, you have to make sure that you're using a filter that is going to pass the light you think it should pass for a system as fast as yours. And they do make some filters that are designed specifically for lower focal ratio scopes. So I had 3s. I found that it was hurting my images, and I actually went up to 5s. So I use 5 nanometer Astrodon filters.
Yeah, Marcia asked about the dual narrowband filters. You have any thoughts about that?
For color imaging, I mean, for one-shot color.
No,
Am I understanding that?
For one-shot narrowband.
Yes, yeah, you're talking about the double band pass or the triple band pass filters that are out. I mean, I'm seeing some amazing pictures with those. I had started out with an SLR, like many people do, and then after that, I got an Astro camera that was a one-shot color, and it didn't work very well. And whether it was my own inexperience or something else, I can't say. But I never used it for very long. But I can say that the pictures that I see that people take with some of these multi-band filters for their color cameras, the cameras produce some amazing images with them.
Do you know any difference between the expensive filters and the less expensive filters?
The thing that seems to come up most often is haloing around and reflections, things like that around bright stars, bright objects, especially. I believe in buy once, cry once. So I just bought Astrodon filters right out of the gate, and that's what I've been using. I haven't had any problems with them, but the people who complain of the people with the less expensive filters seem to be the ones complaining more about haloing. I don't know what any of the experience of others has been like, but that's sort of my understanding.
Thank you. Now, you were going to show us some other stuff. I think we're through with the conversations over there, but if you've got anything else, guys, be sure to just type in your questions over there, and we'll get to them. But let's see some image examples.
Okay. All right. So these are some of the images that I've taken, and these are all I've taken out all the ones that I've done at my dark site. These are all just backyard examples. I'll start by showing you some of the broadband ones. Okay, so these are just going to be RGB or LRGB, and I want to say up front that the struggle in processing these images is controlling the noise and controlling the gradients, the noise and the gradients. That is a problem for almost every image that I process, but especially for my broadband images. But having said that, it's not an impossible situation. It just requires a little bit more work. So here's M108 and M97. So it's the owl and the surfboard. And this is an image that I got, I think, over 2,000 luminance frames. They were 15-second luminance frames, but there was 2,000 of them. And it did a good job of knocking down the noise. What the problem with this image was the gradients. There were some really powerful gradients that had to be tamed in order for this image to be produced. But the noise was great, and the color turned out pretty great too. So I was happy with that. Here's M101. I took this with an 8-inch SCT, and I think noise was the big issue with this one. Markarian's chain, so it's galaxies. Galaxies from a light polluted site are a little bit challenging. So I had gradients and again, noise, despite having a decent amount of integration on this one. Okay, and I mentioned earlier that that I admired all the dusty pictures that people take from their dark locations. Well, here's Pleiades M45 for my backyard, and you can see some of the dust in the back. I think I did capture some of it, but it's nowhere near as as detailed as what can be seen. But you know what? I did it. I did it to the best of my ability for what my sky would allow, and I had a lot of fun doing it. And that's the bottom line. So this is the image that I was able to produce from my backyard of this one. I showed you some of the subframes from this one earlier. This is the M31 finished, and I think I got over 20 hours of integration on this one. Main issue was gradients. And I also noticed, since I've shot this target from a dark side as well, I couldn't bring out some of the faint nebulosity right out here at the edge of the galaxy like I can from my dark side. All right, some narrowband examples. Here's my rosette. This wasn't a particularly long integration, so noise was a factor here. Gradients not quite so much, and this is a Hubble palette or a modified Hubble palette, whatever you want to call it. Okay, and this is a wide field view of the Bubble Nebula, which is up here, Lobster Claw Nebula, again, kind of modified Hubble palette. And you'll notice that I tend to shoot objects to the north whenever I can, just because that's the direction that's favorable in my sky. I like to experiment with color palettes. This is the California Nebula, and the appearance of this nebula has always been one of flame or fire to me. And I noticed by inverting the color channels for hydrogen and sulfur, Hubble palette is usually sulfur, hydrogen, and oxygen for the red, green, and blue channels respectively. So I inverted the hydrogen and the sulfur, and it came out this neat orange flame-like color. So I went with it. I felt like it worked with the flame-like appearance of it. This is the North American Nebula and the Pelican Nebula, and I got quite a lot of data on it, and it's a bright object, and honestly, this one didn't pose that much of a processing challenge. Hubble palette. All right, I tried my hand not too long ago at a planetary nebula. This is the quintessential planetary nebula, M27, and it's a bicolor image, hydrogen and oxygen is what we're seeing here. And you can just make out the faint outer shell. And I took this one with my 10-inch Newtonian. All right, and Alex, I think you might have asked me about this earlier. This was an example of maybe what the limitations of narrowband are. And this is the BAT, right? The BAT Nebula, and then the Squid Nebula inside there. And the BAT Nebula is very heavy in hydrogen alpha. And the the Squid emits light in the oxygen 3. Again, bicolor image, and I collected quite a bit of data for hydrogen alpha, but I really went what I thought was overboard on collecting data for the Squid, and I got over 20 hours, and that seemed to me like it should have been enough. But try as I might, I just could not bring out the detail in the Squid. Like you see images, you see examples of this online, and the Squid just is this incredible, three-dimensional, almost solid-looking object. I just couldn't do it. It was just, this was all I was getting. And no matter how much integration time I threw at it, it just didn't seem to come out any better. So to me, this says that maybe even with narrowband filters, there's a limit to what you can do. So, but like I said before, I'm still having fun, and that's what matters. So I'll continue to take pictures of this, and maybe I'll try my hand at it again. But I just wanted to show you that. And this is one that I recently completed, Elephant Trunk Nebula, Hubble palette, taken with my 10-inch Newtonian and my CMOS mono camera. So, and about 22 hours integration on that. All right. So let me wrap this up. So in conclusion, light pollution hides the night sky from all of us. And it's particularly bothersome for people who want to take pictures of deep sky objects. To overcome the effects of light pollution for astrophotography, you have to optimize your signal to noise ratio. And there's 3 ways of doing that. You can collect photons efficiently or more efficiently with a faster telescope and a sensitive camera. You can collect lots of photons by stacking as many subframes as you can, really accumulating your exposure time to minimize that noise and to enhance that signal. And then for certain objects, collect only the photons that you are interested in, the photons from the target, with the use of narrowband filters. Maximize your time on target using an observatory or peer, or if nothing else, find a way to leave your portable setup out for multiple nights. You will not believe the difference in the amount of data that you can acquire. Hand in hand with that, automate, automate, automate. We have some fantastic session software out these days. Get one, learn it, and automate. Image around a new moon if you can. I image from last quarter through first quarter. Pick a target that makes sense in your sky. And then finally, invest in yourself by sharpening those processing skills. And there's a lot of great resources to do that. And that's it. That's all I have.
Thank you, Glenn. We did have a question come in. Could you, you mentioned earlier about gradients, and Edwin wants to know a little bit about what gradients are. Jeff answered the question a little bit, but maybe if you could say as a presenter from your perspective, what a gradient is.
Can you still see my screen?
Yeah, we're still,
okay.
Well, wait a minute. I don't know. We're still looking at your screen.
Okay.
The YouTube delay tonight is like 25 seconds or something like that, which has been really strange. I've made a few comments on your presentation before you made the presentation, as a matter of fact. So.
Oh, got it. Okay. Well, let me jump back in at this point. Okay. So this was when I was showing you the effects of stacking, and I want you to focus down here on the, the kind of the right lower corner. All right. And for this object or for this session, I mean, that's just where the light pollution was. And that's 1 frame, okay? 2 frames, the object's getting brighter. But look at what's building up over here. Can you see that? And over here, it's getting much brighter in this corner than it is elsewhere in the picture. And then finally, by the time you get to 200 frames, I mean, this is almost as bright as the signal coming from the object itself. So that's what a gradient is. And there's one other example that I think would be instructive. Here you go. So all this green stuff over here, that's all that's unwanted light. That is light that is coming from the sky glow. It is not coming from this target. All right. And that is what we want to get rid of when we process these images. That is the sky gradient that one must deal with when dealing with light pollution. Does that answer the question?
That does answer the question, but I'm going to extend Edwin's question a little bit. What do you do in general about gradient? Well, how do you get rid of them in general, besides taking more pictures?
Right. At some point, you have to deal with it in your processing program. And there are dedicated tools in both Photoshop and PixInsight, AstroPixel processor, and others that tackle these gradients. And there's, I use in PixInsight, I use dynamic background extraction, that process called DBE, you'll hear it referred to. And what that process does, let's say I've got this picture or this image in PixInsight. It asks me to place little sample points it asks me, sorry about that. It asks me to place sample points at various places in my image. So I'm going to put little samples over here because that's some ugly gradient, and over here and over here. And I try to avoid the area where I have useful signal. Okay, so that would be all this red stuff. And then I hit the I hit the do button or the process button, and the software looks at all the sample points and makes a determination about how much of that is from light pollution or unwanted gradient, and then it neutralizes it. It will subtract it out, and it will spit out a version of the image that will have this ugly blue color gone, and the background should hopefully look a lot more neutral. And you can do that. And you can do that in Photoshop. I think there's Gradient Exterminator or something like that. I'm not a heavy Photoshop user, but there's some great tools out there.
Okay, great.
Hey, Glenn, this is Tim. Can I interrupt you with a question, please?
Hey, Tim. Yes, please do.
So I don't mean to put you on the spot, but last week Adam Block was on the show. I don't know if you watched it, but he talked about using the normalized scale gradient as a way to combat gradients and at least make it a consistent gradient and not a more complex one. I've never used it. I was wondering if you had, and if you had any experience with it.
I have not, and I'm halfway through last week's show. I still have to finish it to see what Adam said, but
Okay.
I intend to try it.
Thank you.
Yep.
Yeah.
Well, the other thing you have on that image, that green, we also have SCNR,
Yes.
which will neutralize that
Yes.
almost instantly. The other thing, and this is really a good example of it, emission nebula, when you're that tight on it, the nebulosity and the dust fill the screen, and you've got to be
Right.
really careful
Yes.
about what you subtract and what points you use. It's
Right.
almost better, I would say it's almost better not to do it than to remove some structures in there
Yes.
which are part of the emission.
No, I agree, and there. In fact, I didn't use it. That last example image of the elephant trunk that I showed you, the one at the end of the talk, I didn't use it at all on that, and for that very reason, because everywhere I looked there was nebulosity, and I noticed that when I was first starting out, I put samples everywhere on my image, and it was just peppered with samples all across the gradient. And now I will either do as you just said. I won't do it at all, or sometimes I only will put 2 or 3 samples on the image, just to handle it as gently as possible.
Well, Terry and I have some interesting discussions, and I think we all start out with dynamic background with putting on literally hundreds.
Yeah, exactly.
And use a little tool, 10 per row and
Right.
20 rows.
That's
and
right.
of course, that makes a complete mess. And the reason we don't do it anymore is that gradients are big.
Right.
They're not small. And you're right. A few well-placed points will have it do its job. I think in this image, if you just use SCNR,
Yeah.
you probably wouldn't muck around with DBE at all.
Right.
SCNR can be detrimental to narrowband images. If you have a lovely teal in there,
Right.
it will change the color. That's not correct. So just be careful where you use each tool. That's all.
And when I approach an image, just to finish up on that, when I approach my processing, I will, I'll try SCNR, and then I'll try another one, and then I'll try, a different technique with DBE, and I'll trial a bunch of things and see which one works best for that particular image. And sometimes it's a tool like SCNR, and other times it's DBE, and other times it's don't use any of those.
Okay, we've got a question from Glenn, for Glenn. He only has one N in his name. You've got 2.
How dare he?
Anyway, he says, do you use any light pollution filters for RGB?
I don't shoot one-shot color. So when I think light pollution filter, in the context I think that he means it, I think that applies more to a one-shot color camera. They do make specialized light pollution filters for those kinds of cameras. But in essence, I mean, a narrowband filter or any, a narrowband filter in particular, I mean, it's a very, very strong light pollution filter. You're filtering out tons of light pollution. And, that's not necessarily what you're looking for, but in effect, it's doing just that. It's filtering out all the light pollution and showing you just the signal from your target.
Okay. Yeah, you have to understand what's going on when you're filtering with a light pollution filter. You're letting some stuff in and other stuff you're not letting in.
That's right.
And with the narrow band, you're already not letting nearly everything in.
Right.
You've just got one very small strip.
And I will say for a light pollution filter, those probably had more relevance back in the days before LED lighting. When you had sodium, what do they call it? Sodium lighting.
Yeah.
There were specific
halogen and
right. There were specific parts of the spectrum that kind of lighting lived in, and these filters would cut that out. But now with broad spectrum LED lighting, I think it's less effective.
Yeah. And the world of tri-band and dual band filters for one-shot color is much different than the world that we're talking about with mono and narrow bands. So some of the concepts apply, but there are different things going on. And then after you've cut out XYZ bands of the spectrum, then you've got to get through the Bayer matrix, which is already cutting out other parts of the spectrum. So I don't have enough experience to comment on the effectiveness of it. Maybe out there somebody does have such experience and they can offer a program on the Astro Imaging channel.
There you go.
Yeah. How we doing? We got all the questions, I think. We're all caught up, right, Eric?
I'm looking. I don't see anything new.
And we've got a few congratulations. Nice shows showing up already.
Awesome. Thank you. Thank you.
And so I want to thank you for putting on the presentation. If you could stop sharing your screen and just come on back live to us, that'd be cool. And what else am I going to say? I don't know. So I think we're ready to call it a night. We got everything taken care of. Don't forget, we need you to turn in your nebula that you've been taking pictures of. We need you to go on over and catch up on the workshops, get Eric's data, process it, and show us how you can do things. And I think we're good. Tim, I think you're in charge tonight. Glenn, thank you so much for being here tonight and
thanks for having
your
me.
services.
It was fun.
And I should tell everybody here, it might be a little personal, but Glenn remarked to me, I asked him to do this show, I don't know, a couple months back, and he says, I guess I can do it. And you guys can do it too. I mean, all of you can do a show. All of you've got something you can share with other people. You're all bright people. You're all astro imagers, so you know how to handle stuff. Volunteer to give a show. You can help people a lot. Okay. Thanks, everybody. Tim, take us out.